A rainbow is a most beautiful thing to behold, but if it weren't for light and how it behaves, we wouldn't be able to see it. Raindrops act like a prism, splitting the combined white light from the sun into all the physical colors of the light spectrum. But even the colors of simple things, like a leaf for example, have to do with wavelengths of light. Each color in light has a different wavelength, so when light reaches an object, some wavelengths get absorbed and others get reflected back. We only see the reflected colors. A green leaf only appears green because all the other colors have been absorbed. It is this same principle of color and wavelength that a spectrophotometer is based on. A spectrophotometer is a special instrument that measures how much light a substance absorbs. Every substance will transmit, reflect back, and absorb light slightly differently, like how a fingerprint identifies each individual human, knowing exactly how much red, or green or blue, etc., gets absorbed allows us to identify and quantify different materials. So how does a spectrophotometer work? What's going on inside the box? 1. A sample solution is placed inside the spectrophotometer. 2. A light source shines light towards the sample. 3. A device called a monochromator splits the light into each color, or rather individual wavelengths, just like a raindrop makes a rainbow. An adjustable slit allows only one specific wavelength of light through to the sample solution. The wavelength of light hits the sample, which is held in a little container called a cuvette. We need to be careful when handling cuvettes. Even a slight fingerprint can interfere with the results. Whatever light passes through the sample is read and displayed on the output screen. Before the spectrophotometer was developed, scientists had no reliable and rapid method to determine the chemical makeup of a substance. The spectrophotometer radically changed all of that. You can imagine how useful it could be to know what is in a substance. A spectrophotometer is used in many areas of science, including microbiology, biochemistry, forensics, physics, and medical health. You can use it to measure certain ingredients in a drug to make sure it is effective and safe for consumers. You can measure bacterial growth, or diagnose a patient based on how much uric acid is present in their urine. Even non-scientists use spectrophotometers. Winemakers, for example, use them to determine how much malic acid, or reducing sugars, a particular wine has in it. Scientists can use the spectrophotometer to see how a reaction has progressed. Let's say you're studying iron deficiency, a condition that affects over 2 billion people. Antioxidants, vitamins, and other agents are known to help in iron deficiency, but they don't have a single specific chemical makeup, so they can't be directly measured. However, they are known to reduce ferric iron into ferrous iron, a more valuable form to the human body. Ferrous iron will have a blue color, while ferric iron will not. Mix in ferric iron into your sample solution of whatever product, and then measure the intensity of blue created with a spectrophotometer. By setting it to 593 nanometers, the exact wavelength of the blue color that pure ferrous iron reflects, and measuring how many waves pass through, you can know how concentrated antioxidants were in the mixture. The amount of light that makes it through the substance is displayed on the output screen and is called absorbance. In order for this number to mean anything, we need a standard curve. A standard curve is determined by recording the absorbance of known concentrations of a material. Let's say we had 3 known solutions of ferrous iron. One has 5 parts per million ppm ferrous iron, the second 10 parts per million, and the third 15 parts per million. The 5 parts per million gave an absorbance of 0.5, the 10 parts per million gave an absorbance of 0.8, and the 15 parts per million gave an absorbance of 1.1. We can make a graph with each of these points and then draw a line that connects all 3 dots. If our unknown sample gives an absorbance of 0.9, we can look on our line and know that it falls between 10 parts per million and 15 parts per million. Further calculations can determine with greater accuracy how much ferrous iron is in the sample. The basic spectrophotometer just uses the visible light spectrum, wavelengths from about 400 to 700 nanometers. But some materials are better understood outside that range. DNA, for example, is best at absorbing wavelengths of 260 nanometers ultraviolet light. Ultraviolet and infrared spectrophotometers have 2 or 3 light sources and can emit and read a wider spectrum. UV spectroscopy is important for ethanol analysis. Ethanol absorbs visible light wavelengths very weakly, but can easily absorb UV light. Infrared spectroscopy is useful in many organic settings, like determining materials in human blood. A spectrophotometer measures the amount of light transmitted through a substance and is an invaluable instrument in science. Without it, determining the chemical makeup of materials would be very difficult and not very accurate. It uses a light, a monochromator, which separates light into individual colors, and a container called a cuvette to display the resulting absorbance on a monitor. Since every material reflects a specific wavelength differently, we can identify and quantify unknown materials in a sample or measure changes in a reaction. Some spectrophotometers can emit and read UV and infrared wavelengths as well. These amazing devices are used in a wide array of sciences, including medical health, physics, forensics, microbiology, and biochemistry.